If you're the kind of person who likes to have things written out in detail, I thought to save some time that I would give you this handout so you've got this written down. You can refer to it. It's got nice little things like, well, we'll get to it, I guess, but come on. Functions cannot cross a vertical asymptote. So there you've got like a solid record of this is something that can't happen. You should never be drawing a graph, and I've seen it for sure, where the function crosses a vertical asymptote. That is not possible. A vertical asymptote occurs because the denominator is 0. So there's no way to evaluate that function and figure out what it equals. Like, think about what a function is. Think about what a graph is. The y value of graph is just where you evaluate it when you sub in that value of x. If the denominator is 0, it's not possible no matter what you do. That is different from a horizontal asymptote that can be crossed. Because I can cross it in some places, but then it won't others. Eventually they'll settle in. Anyway, so there's like, we're going to go over this, but there's concrete notes that if you like it, you can refer to it on this handout, okay? So sketches will include, on a quiz typically or a test, we will tell you what's expected for a sketch. But basically, we're looking for what we're able to do, right? So it's like the minimum that we can do is probably what we are going to ask you to do. But anyway, at this point, we can find intercepts, all intercepts, right? So that's always something that we do. We have added in critical values as something that now we can do with calculus with the derivative. The end behavior, that's just like generally where do the ends go of a polynomial or anything like that. And then when we start to look at rational functions, we are adding in asymptotes, and then around asymptotes we have different kinds of like end behavior or asymptotic behavior, so we're going to add that. That's what we're adding in today. Okay? A vertical asymptote occurs when the denominator in a function evaluates to 0. So that's how we find it. And again, if you like steps, if you're just trying to memorize, which is not a great way of doing things, but if, sometimes it's fine to do that in some cases, this is what you do. Where do I find the vertical asymptotes? I find out where the denominator is 0. That's how you find the vertical asymptotes, okay? We're going to use some new notation today to do this. It's the same idea that we did in MHF, but we're going to try it with a bit of a new notation because we have limit notation now, which we didn't used to have. Although that being said, if you use the old notation, that would, as long as you did it correctly, that would probably be fine. Okay. We are going to include vertical asymptotes in the first column of the derivative chart. You'll see what that means when we get there, but it's important to include them. They are like critical values that we consider throughout the process. We've already done that when we were doing derivatives. Where is the derivative 0? Where does it not exist, right? We've already talked about that. And where it doesn't exist, maybe a local max or min. In our case, it's going to be an asymptote, but we still want to consider it. And because we've talked about how a graph can be increasing before an asymptote and decreasing after, so that's like we're breaking up the interval. That's what the derivative chart is all the intervals. Does that make sense? If it doesn't, you'll see when we do an example of what that looks like. Just quickly, what are some of the ways that asymptotes can look like? So when we explore the asymptotic behavior, we're going to get something like, as it approaches from the left, it's going to positive infinity. As it's approaching from the right, it's going to negative infinity. And then maybe again, as it's approaching from the left, it goes to negative infinity. And when it approaches from the right, it goes to positive infinity and positive infinity. Something like that. It may also do something more like this. And really, again, so maybe it goes down like this from this side, and then it's both up like that, and then this one's down again. Like, it could be any of those combinations. You might have more than 2 vertical asymptotes. You might only have 1 vertical asymptote. All those things are possible. We're going to look at oblique asymptotes unless we run out of time today as well. And it's kind of a review of what we did in MHF. A lot of today is review of what we did in MHF, okay? But for you, drawing graphs is about drawing all the kinds of graphs, not just the ones you've seen in class. So I will tell you this, in the practice, there are probably some a little bit different from any you've ever seen. But the whole point of this process is to put you in a position that you can draw those kinds of graphs too, that you can determine what the end behavior around the asymptotes is from the process. Not that you're just like matching, oh, it's this kind of graph or it's this kind of graph. Does that make sense? I hope that makes sense. So those are some of the ways. And then you add in horizontal asymptote like this, and maybe it approaches from the top there. And this one would then cross the horizontal asymptote, and this one might cross and then approach from the bottom or something, right? Like there's all different kinds of things that could happen with horizontal asymptotes as well, and just with graphs in general. Okay, they're all a little bit different. Again, I already said functions cannot cross vertical asymptotes. Ever, 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 ever. Okay? If you go to university and your professor finds a graph where that does happen, come back and show it to me because I'll be interested to see it. There's a lot of math I've never seen in my life, so maybe it's possible, but I don't think so. And definitely in high school, it's not possible. Okay, horizontal asymptotes. This is the behavior at the extreme ends of the graph, and we're talking horizontally, hopefully obviously, right? Because functions can cross horizontal asymptotes. We're looking at the behavior at the extreme ends. The rational graphs and other graphs, exponential graphs and that sort of thing, and lots of other different kinds of graphs, will settle into some kind of behavior as they get far out horizontally. So they do all kinds of wonky things in the middle. For us, it's usually around the origin because that makes it easy to sketch. Otherwise, we wouldn't be able to sketch it. And then eventually settles into some kind of approaching a horizontal asymptote. Okay? And so that's what we're checking, is what's happening as we go out far. So what we do is we sub in something like f at negative 100 and f at positive 100, and we figure out what those equal, and then we compare it to the horizontal asymptote that we've already determined. The test for horizontal asymptotes is absolutely different from the test for vertical asymptotes. And some people do struggle and mix those up, and then everything falls apart. Okay, so make sure you know the difference between the two tests. This is the one for horizontal. When we do other kinds of functions, it might not be 100 and negative 100, because things like logarithmic or exponential functions grow very differently from these. And so putting in 100 wouldn't work for some exponential functions. So we wouldn't want to use that value, but we'll get to that way down the road. So for now, for this unit, that would be our typical test, our chosen values. Plug in those two and see what happens and compare it to the horizontal asymptote. Again, this is very different from the test we're going to do with vertical asymptotes. Okay. And so here's when the horizontal asymptotes occur. Now, there's different ways of thinking about this. And as we go through the examples today, I'll try to point those out. And then I think that's a better way to memorize, or a better way to understand and figure this out than just to memorize this rule, that horizontal asymptote occur when the numerator, that means the number on top, and denominator of a function have the same degree. Like if you memorize that, I mean, good luck. But after we've gone through this and you've done some of the practice, hopefully there's a couple of tricks that will help you remember when they happen. That being said, when they have the same degree, we get a horizontal asymptote of the form y equals b, where b is some number, a fraction, an integer, positive, negative, anything. Horizontal asymptotes also occur when the degree of the denominator is greater than the degree of the numerator, and in each of those cases, no matter how much greater, you get a horizontal asymptote of y equals 0. And I would remember that back from grade 11 when you did this graph. The degree of the denominator is higher than the degree of the numerator, as long as you don't have like a +1 outside, okay? Then you get a horizontal asymptote of y equals 0. Okay, and that's what you had there. So there's those two kind of options. And this is directly, but that one is directly opposite from oblique asymptotes, and that's why people mix it up. But there's a trick for remembering when it's an oblique asymptote. We'll get to that. And if I knew that trick, that allows me to figure out kind of easily all the other stuff about horizontal asymptotes. We can check whether the function is above or below horizontal asymptote by substituting a large number into x. That's what we just talked about. Our numbers are going to be negative 100 and 100. And we only need those two because you only have typically one horizontal asymptote, and we just need to check it at both extremes. It is possible to have a horizontal asymptote at one number on one side of the graph and a different number at a different side of the graph, but I don't think it really comes up for us. And if it does, we'll talk about it when we get there, and it's like a different case. So for the most part, that's not something we need to worry about. For the most part, horizontal asymptote will just be the same across the whole graph. Okay, and we're going to talk about oblique asymptotes, I think, when we get there, but we can just point out quickly, occurs when the degree of the numerator, actually, why not? We'll just talk about it, why not? Is exactly one more than the degree of the denominator. If the degree of the numerator is more than the degree of the denominator, you understand what I mean by that? It's an awkward sentence, but so if this degree was 3, you would have a different kind of asymptote. It would actually be like a curved asymptote, and we don't talk about those. So for us, we only look at this case. You won't get it where it's 2 more or 3 more. You could graph it in GeoGebra and see what it looks like. It's really interesting, but that's not what we're looking at right now, okay? And this is how I can tell that it's an oblique asymptote, because we're going to do division, synthetic division, long division, and I'm going to do this divided by this. And I can't do that if it's reversed. If the bigger degree is on the bottom, you can't do the division. Like, what would that look like? That would be really wonky. I mean, you could do it, but you would get strange things happening, right? So if the lower degree is on the bottom, I can do synthetic division. I can do 2x squared minus blah, blah, blah divided by x minus 2. And when you can do it, that means you're doing it because it's an oblique asymptote. That's my trick for remembering which is which. Okay, and we'll go over the rest of that when we get there. Any questions? We might refer back to all of that good stuff, but that handout is for you if you like to have structure and concrete written down. When this happens, then I do this. When this happens, then I do this. That handout is good for that, which maybe you don't have that handout. Is that true? Useful to have? There you go. Okay, good? First question, we're not doing a full sketch. We're just determining the asymptotic behavior of this function. And we're going to start with the vertical asymptotes, and then we're going to do horizontal asymptotes after that. I like to do this. Sometimes questions are given y equals. Sometimes they're given f at x equals. It's kind of interchangeable. But I would say it would be a little strange if you were given a question like this, and then all of a sudden you're like, f at 100 equals, like, what are you talking about? What's f? So when this happens, you really do need to add a little let f at x, and it's equal y. I don't even have to write out the whole function. I'll just say y, because y is the function, right? So let f at x equal y, and I'm done, and I'm fair game to use either notation throughout the rest of my question, okay? So I think that's a really good thing to do at the beginning. There are other ways you can show the notation. Mr. Gardner shows some of it a little bit of a different way. You could do that as well. He shows ordered pair points. I like to use function notation. You could do it whatever way as long as you're clear. That is maybe a hard part of the curve sketching is it's a huge process, as you know from MHF. These are big questions that take 20 minutes to do sometimes. And there's a lot of steps, and showing your work clearly is a big part of what you're coming to terms with, okay? Often what we would do as a starting point is, so we're going to do it here because why not? But I'm going to talk a little bit fluidly about some of these steps, and a big part of what you're going to do over the next week as we're doing curve sketching for like a week, basically the rest of this unit, is you have to get good at figuring out the way you like to do these steps. There's different ways of doing it, and this is what I'm trying to say. There's not time for me to show you all of them and all the different kinds of questions that you're going to come across. So you have to be able to be doing the practice to kind of be figuring it out as you go, all the different things that can happen. So for example, what if the numerator wasn't factorable? And I think this one is b squared minus 4ac, I believe works out. So let's try to factor it. So y equals, I've got 3x and x on top, and I'm obviously going to have 1 and 1. And it works out to plus and minus, is that right? 3x minus 1x positive 2x, we're good. And I'll factor the bottom as well, because why not? So here's my point. We're doing an example today that's factorable. But what if in the homework one of them is not factorable? Well, that's the point of the homework, is that you go practice them and you see if you have questions. Okay, and you see what it's like. Some of the evaluating is very different when it's not factorable. And every question might be very different. And some of it's awkward and it's nasty. It's like, it's messy. And we tend to work in math class to go towards the most efficient and eloquent methods of doing things. And there's no nice way of doing these things, unfortunately. So we just have to struggle through it. Okay? So that's what we're going to do. You look like me. We should hang out later. All right. Okay, so vertical asymptotes. What did we say about vertical asymptotes from our sheet? They occur when the denominator equals 0. Because I have the denominator in factored form, that's an easy thing to see. So I've got a vertical asymptote of x equals positive 2 and x equals negative 2. I almost always work from left to right in my head because, for one, that's how I learned to read, and so it makes it a little bit easier on me, and it's just a good habit to have a way that you're kind of always doing things. And if you don't do it that way, I think there's a little bit of extra thinking, well, wait, which one is this? Which one is this? And as you're sketching your graph, we do all this work to get all the details before we actually sketch the graph. And if things are out of order, it's that much harder to sketch the graph. So I would strongly encourage you to pick a way. Now, it doesn't have to be the same way as me, but I would strongly encourage you to pick a way of doing it. I'll always do it left to right, and that's just my rule of thumb. It does take some load off my working memory, and it's just a nice habit. So right there, I already broke that because I didn't do my vertical asymptotes left to right. But we're going to do our x equals negative 2 vertical asymptote first. Now, I'm just remembering that I want to conserve some space here because if I write too big, I'm going to run out of space. And I'm going to be kind of, like I put a little title here of what this is. You don't have to do that, but I'm doing it for the lesson so that we're nice and clear. So here's the new notation. I don't think we showed our work this way in MHF because I don't think we had this notation yet when we were doing our curve sketching. We talk about the limit as x approaches negative 2 from the left of f at x or of y. What is that? And then the limit as x approaches negative 2 from the right of y. And remember, some people, sorry, I'm going to get rid of that, of y equals. Some people just do this. And that's not a thing. Okay? That's like, I'm taking the square root of well, you square root of what? You got to have something in here, right? So same thing, you got to have something in here. So it's the limit as x approaches negative 2 from the right of y. What does that equal? And then for my other asymptote, the limit as x approaches positive 2 from the left of y, what does that equal? And the limit as x approaches positive 2 from the right of y, what does that equal? And we've got two asymptotes. So it approaches from the left, it approaches from the right. The other one approaches from the left, approaches from the right. So we should have 4 values that we're getting here, figuring out what happens. This is where, depending on the particular function, the next steps are going to look different in your head. You can nitty-gritty pick a number that's very close to -2 from the left and plug it into the equation and just work it out. It's a little bit slower, but if that's what you end up needing to do, that's what you do. And then from the right. So what would I pick for this one? Just to the left of -2, -2.1. What would I pick for this? -1.9. That's just to the right of -2. Make sure you don't get your backwards because you're doing negative. And then for this one would be +1.9 is just to the left. +2.1 is just to the right. And that's what it looked like in MHF. We did this. F at -2.1 equals F at da-da-da-da, right? That's what we did before, something along those lines. So now we're using limit notation. And then what do I do with that? Well, I take it and I plug it in. So here's what I'm doing. And again, this looks different. Every question, it looks a little bit different. And this is part of what I think you need to get good at. It might look a little bit like magic. Somebody who's good at doing math in their head doing this. You're like, whoa, I didn't follow that. I was too fast. What did he do there? Go back and watch the video. Go back and think about it yourself. Okay, this can be tricky for some people. For some people, they're not so bad at it. So I'm taking something just a bit more negative, a bit bigger than 2, bigger negative. And I'm putting in here, when I square it, it's going to be positive. So it's going to be bigger than 4. So when I subtract 4, I get a positive. So for this one, my denominator is positive. And then what I'm actually going to do to save myself some work is I'm just going to put 2 in here. Now that might seem weird, and if you don't like it, that's fine. Then because this is factorable, you can use -2.1 and plug it in there and see what happens. But like I said, sometimes it might not be factorable, so it's different. And we did a lot in MHF that are factorable, so that's why I'm doing this one. I'm using this top part. It's probably less efficient, but I'm doing that anyway. So 2 squared is 4 times 3 is 12, plus 2 times 2, so that's 16 minus 1 is 15, so positive 15. So if I put in, oh wait, that was wrong, because this was supposed to be negative, sorry, but it's still going to work out to be positive. So I get 12 minus 4 is 8 minus 1, I think is 7. That's right, because I'm plugging in a negative number. So I get 7, but if I plugged in -2.1, it's going to be basically the same. It's not going to change it that much. So I've got a positive over a positive, and all I care about is that we're going to positive infinity. And again, this is different from horizontal asymptotes. Horizontal asymptotes, I need to know the exact value. But vertical asymptotes, I only need to know if it's going to be positive or negative. When I put a number that is slightly smaller than -2, well, the top is still going to be the same. That's not really going to change the top. So we said the top was positive, but what it is going to do is it is going to change the bottom, because now I'm going to get something, when I square it, I'm going to get something slightly smaller than 4. When I subtract 4, I get a negative. So this one's going to be negative infinity. And this is what I'm talking about. If anybody didn't follow that, go back and think about it again. That is something you need to be able to do in your head, or just punch it into your calculator. Whoops. And you can also ask me about it later. Okay. And then I do the exact same process for +2. And if I put in a positive number, the top is obviously positive, I hope. And if I put in 1.9, same thing, the bottom is going to be negative. So this one's going to work out to negative. And then this one's going to work out to positive. Is everybody okay with that? And if you've done it enough times, you start to be able to do it faster and faster and faster. It makes your job so much easier. And, I really noticed that these two were very similar and these two were very similar. And that's something that maybe until you have experience, you might not see that. Again, this is what you will be working on throughout the practice. So what have I determined so far from this? I've got an asymptote at -2. I've got an asymptote at +2. And I determined that as I approach negative, this is where I go left to right again. Because I use that standard for myself, I know that these are written left to right. And I just go from left, it goes to positive infinity. From the right, it goes to negative infinity. From the left, it goes to negative infinity. And from the right, it goes to positive infinity. Okay? Okay, and now we're going to do horizontal asymptotes. How do I find the horizontal asymptote of this function? There's a nice little, I did an interesting activity with my MHF class last semester to explore this, where it comes from. And if you're curious to see that, we can look back at it or you can ask me about it. There's a really beautiful algebraic way of looking at it, and maybe we'll do that later if we have time. We don't have time today. Okay. Does anybody remember where it comes from? Yeah, that's fine. Right? So we look at the coefficients of the highest degree terms. Remember, if this was a degree smaller, if it was a linear over a quadratic or a degree 1 over a degree 2, then technically the degree 2 of the top is 0. It'd be 0x squared. So that's why the horizontal asymptote would be 0. But otherwise, it's, and if they're not in the same order, you got to rewrite them. It's the coefficient of the highest degree term on top over the highest degree term on top on the bottom. And they are the same degree. Okay? So degree 2 over degree 2, which is 3 over 1. So our horizontal asymptote, is y equals 3. 3 over 1 or 3. Okay? I do f at negative 100 and f at positive 100. And I just work those out. And I probably will plug those into the factored form if it factors, because that's usually an easy way. Like negative 100 times 3 is negative 300, minus 1 is negative 301. So I can do that part in my head, and in my calculator, just punch in negative 301 times negative 99, right? But for us, because we don't have a lot of time today, it works out to 2.98. You can check that later if you want. I think that would be a good idea. And then this one works out to approximately 3.02. And this is why I need the exact value. Everybody eyes up, look at this. What can I conclude? Therefore, this is below. Therefore, this is above. Because look, 2.98 is just below 3, and 3.02 is just above 3. It's not always one or the other. They could both be below. They could both be above. They could be the opposite of this. Anything could happen. That's what we're trying to determine. Oblique asymptotes, we're trying to determine if they're above and below, but that process is a little bit different. We okay with this? So we have to compare it to the horizontal asymptote. I'm not just looking for the sign. They're both positive. The sign doesn't help me because the horizontal asymptote is positive. If the horizontal asymptote was 0, you'd get away with positive, negative. But that's not the idea. My asymptote was y equals 3. And take a look from the, when I want to go out to the left, the extreme left, I'm below. And look at where it's coming from. So this is one of those cases where my graph crosses and approaches from below. Sometimes that happens. It looks like in this case that's what would be happening. And on the other side, it's approaching from above. So like that. Any questions? Are we sure? So there's your quick review on vertical. And we haven't even added anything. That was all from MHF. I think same thing with this one. We're going to determine the asymptotic behavior of this one, just the oblique. I don't think we have time to do the vertical. It has a vertical, obviously. Here's another rule. I don't think this was on our sheet. You can add it if you want. You can add it now or add it later. Functions never have oblique asymptote and horizontal asymptote. Okay? They never have that. You can think about why that's not possible. Think about where a horizontal asymptote comes from, and when a horizontal asymptote is y equals 0, and extend that to this process. That'd be a good thinking exercise. Okay, can't have that. So once I determine that I have an oblique asymptote, there's no horizontal asymptotes, but there's probably, almost certainly, vertical asymptote. Maybe even there is certainly, I don't know. So how do I recognize this as an oblique asymptote? Well, the degree of the numerator is 1 more than the degree of the denominator. So I'm going to make a note to myself that it has an oblique asymptote. Typically, when we do a curve sketch, we do the asymptotes later, so we start with intercepts and that kind of thing. But I don't want to forget about the oblique asymptote. Again, I'm going to let f at x equal y, just so I can use that notation, which, again, I like to in this process. Okay. And here we go. What are we going to do to find the oblique asymptote? We're going to do the division. So I can do synthetic in this case. In every question, you can't do synthetic, so you may have to do long division. So I'm actually going to do the long division just to walk you back through it. You can try the synthetic now and look over the long division to remember how to do it later. Again, you can ask me if you want to see it in detail. X goes into 2x squared is how I would do that, right? If you're watching, I do, and then I do this times this to get that term. And then I subtract. So negative 7x minus negative 4x is negative 3x. This 3 comes down. Three minus 6 is negative 3. And here's the synthetic. If you do that part, 2, negative 7, and 3. So I bring the 2 down. Whoops. Bring it down a little further. And multiply. And it's really, by this point, these two questions actually really show what synthetic division is doing. It's just doing the subtraction of the long division minus all the other stuff, just noticing that pattern, right? If you compare those two, you can probably figure out what synthetic division is doing very easily. So there you go, and then I'm going to read my answer, and I'm going to do this. Therefore, y equals 2x minus 3. That came from either there or there, right? 2x minus 3. You have to know how to read the answer for synthetic division. That's from MHF. Plus the remainder over the divisor, the thing we were dividing by, which is the denominator of the original function. I just want to go over where this comes from because I think it's really important, but you don't need to do this every time. But remember, so I'm doing this off to the side. 2x squared, this was the original question, minus 7x plus 3. Oh, shoot, I'm going to run out of space. Go down to the bottom of the page and do it. 2x squared minus 7x plus 3 over x minus 2. Oh, no, just like that. When we did the division, when you first learned to do long division and synthetic division, what we realized is that we were figuring out that this is equal to x minus 2 times 2x minus 3, the divisor, times the quotient, plus the remainder. Right? That's what it works out to. And if you do like division of 21 divided by 5, it's 5 times 4 plus 1. That's what it is, right? If I divide both sides now by x minus 2, what happens? Well, on the left, I get that function. f of x or y. And on the right, I get this bracket times 2x minus 3 over that same bracket, and they cancel minus or plus negative 3 over x minus 2. And I get the function that we just wrote up here. So you can, again, you can memorize that step, but if you kind of get it, it helps. Okay, and then I'm going to state that my oblique, whoops, I'm not going to use a different color, my oblique asymptote is y equals 2x minus 3. And my remainder, and I'm going to give that a new function name because that's going to be useful in just the next step, is this, negative 3 over x minus 2. That's why I did, if you just want to watch quickly, added negative 3 over. If negative 3 is the remainder, it's got to be there in that final part, right? And very quickly, I'm going to use my remainder, whoops. I'm going to use my remainder to test the behavior. And again, this is tricky. We did this in MHF, so if you want to see it again, come and talk to me. But this is like a horizontal asymptote, and since an oblique asymptote is in place of a horizontal asymptote, that might be something that you can figure out. And I'm just going to punch it in, and in this case, we do only care if it's positive or negative. So the top is negative, the bottom is negative. I can see that easily. If the bottom was quadratic, there would be more work there. But the bottom is linear, so it's easy. So it's a negative over a negative. So r at negative 100 is going to be greater than 0. Or I could say is equal to a positive. Like you can say that however you want. Therefore, it's above. And then when I put in 100, I get a negative over a positive. So it's less than 0 or it equals a negative. Therefore, it's below. And so this is what this means. This is something that people have a hard time with all the way back to grade 9. How do I graph my oblique asymptote? Well, there's your y-intercept. It's negative 3, so I go down to 3, and it has a slope of positive 2. That's up 2 over 1, up 2 over 1, up 2 over 1. It's slanting this direction. So there's my oblique asymptote. Make sure you know how to graph a line. And what this is saying, take a look, this is a really cool thing to think about, a really cool thing to visualize, is this function is saying that I take this line, that's a line we just graphed, and for a big value of x, I add this. So if it's positive, I'm adding a tiny bit, so I'm just above that line. If it's negative, I'm taking away a little bit, so I'm just below that line. That's why this works. So when I go to negative 100, I'm just above. And when I go to positive 100, I'm just below. So that's what that means. Any questions? Okay, in 5 minutes, do you think we can get a sketch done? I don't think we can. So I'll do this, and I'll put it up online, and you can try to watch the video. I'll try to do it as soon as I can in case you have MSIP soon and you're trying to work on it. And or you can just look over the thing. The only thing that's different is after we do the intercepts, we do the vertical asymptotes, we do the oblique asymptote, but then we have to do the critical values table. This is what I'm talking about. You would get a question on a test that said, sketch the following considering intercepts, asymptotes, and critical values. Right? It'll tell you what you have to consider. But it's basically will usually be everything that we can do. And the critical, so we didn't look at intercepts, but we kind of know how to do that. Asymptotes, we just looked at, we reviewed that. It's from MHF. And critical values is what we've been doing. So we're just putting it all together, what we've been doing over the last few days. Okay? Yes? The vertical asymptote will be in the critical values table, which is what we were like doing yesterday. So it'll be one of those values exactly. And it'll be one of those things where When we've done the derivative, we're going to state where the derivative is equal to 0 and where it does not exist. And those go into my critical value table. Right, so we state those things and go in, but I'll show you that afterwards. There's your practice, 362, number 9. Oh, we have time. We got 3 minutes. We could talk about this. Some notes. This is what I was talking about throughout. Determining behavior is very different for different, I think, for different numerators and different denominators. And so if you don't do the practice, you may not have the experience of the different kinds of things that might happen. What if I plug in a negative here? What if I plug in a negative there? What does it look like in this case? What does it look like in that case? Also, there are many different shapes of graphs. Some you saw in MHF, some you haven't, some you see in lessons, some you don't. And your goal is not just to be able to recreate ones you've already seen. So it's fair game that we might put on a quiz or a test something that's slightly different than what you've seen. We would do that on purpose. The whole point of this is you're building a picture in your head of the graph. Okay? Not just the ones we've done in class or done in the homework. So keep that in mind. I think there's 6 sketches in there. So, maybe you set up a few of them and sketch a few of them, or make sure you do a few that are different. Make sure you do at least one that has an oblique asymptote and do a few of them. 6 is a lot. I recognize that. Maybe do a couple of them, a few of them tonight, and leave a couple of them to another day where you have more time. I don't know about that. I realize it's a lot, but as I said, you got to practice different types. So eventually it's important that you try a different one. Okay, here we go. So we're going to put it all together now, and we're going to do a full sketch, and we're going to consider the intercepts, asymptotes, and critical values. And we usually do it in that order just because, well, it's kind of the order of difficulty, I suppose. We start with intercepts. And part of this process, because it's such a big process and there's so many steps, is that you're very clear in what you're doing. So little titles like this go a long way towards making sure that your solution is clear. That's not just for the people reading it, but it's also for yourself so that you remember what you're doing and that sort of thing. So y-intercept occurs when x equals 0. So this is easy. I just plug 0 in and I get 0 over something. So my y-intercept equals 0. And my x-intercept occurs when y equals 0. And when y equals 0 is when the numerator, the top, equals 0. So this is when 16x equals 0. And this was hopefully obvious because if I have a y-intercept that's 0, I got an x-intercept that's 0, right? That's the whole point. And we only have 1 in this case. Often we have more than that, but in this case we only have that 1. So that's done. On to asymptotes. And I'm going to start with the vertical asymptotes. And the vertical asymptotes are, there's only one, and it's at x equals -4. That's the only value that's going to make the denominator equal to 0. And again, often we have more than that, but in this case, this is a bit of a simple one, simpler sketch. And it only has the 1. So, and don't forget my let f at x equal y. Okay, I may or may not need that. We'll see. I think I will probably use that, but it's just a nice little habit. A limit as x approaches -4 from the left of y equals, and the limit as x approaches -4 from the right of y equals. So when I put something that's negative in, again, this is how everyone's different. Both of those, it's just a bit past -4 or just a bit before -4. Those are both negative numbers. So when I multiply them on top, the top's going to be negative. And no matter what happens to the bottom I squared, it's going to be positive. So right there, when I analyze this function, I realize that both of these are going to be negative. Now, you may do it that way. You may not. As I said before, you could pick -4.1 and -3.9 and actually plug them in and evaluate them and see what you get. But in both cases, they're going to trend to -infinity. Okay, so that part's done. horizontal asymptote. When I look, I see that the denominator has a degree of 2, so it's more than the numerator. So my horizontal asymptote is y equals 0. And I'm going to do f at negative 100 and f at positive 100. And when I plug this one into my calculator, this is one where you actually need to evaluate these with some calculator work. You're not doing these in your head, and we're not just worried about the sign. In this case, we actually kind of get away with that. But I think you'd have a hard time figuring that out in a lot of cases. So this one works out to be negative, and this one works out to be positive. And again, I shouldn't have even said that. We care about the actual value there, because I usually have to compare that to the horizontal asymptote to see if it's directly above or directly below. So this one, negative 0.17, is just below 0. And positive 0.15 is just above. Okay. So that was pretty simple to get through the intercepts and the asymptotes for this question. We're going to move on to the critical values, which is the part that we're adding. So for the critical values, I have to find the derivative. And this was the original function, 16x over x plus 4 all squared. Quotient rule for these ones, quite different from the polynomials we're doing in the past. So, you know, one thing that you got to know about this course is you have to be able to find the derivative. This is all we do for the rest of the course, is take derivatives of things. And when we get into trigonometry and exponential functions, there are different rules, but you still need to know all of them. So it's really important that if you're still making mistakes taking derivatives, that you go back and do the practice and brush up, because you just have to be able to take the derivative and get it done correctly to be successful. So the derivative of the top times the bottom minus the derivative of the bottom times the top. So I'm going to start with 16x, and the derivative of the bottom is 2 times x plus 4 to the 1, and then times the derivative of what's inside. In this case, I don't need it, but I am always doing that. And then there are certainly cases where when you do the derivative of what's inside, there's something there that's an easy thing for people to miss. So it is times 1, because that's the derivative of x plus 4. And then over the bottom squared. So x plus 4 squared is to the 4th. Okay? Now I'm going to factor. This is the best way to do this. If you expand and simplify, that's going to take a lot more work. So the best thing to do here is to factor this. So I can factor out a 16, and I can factor out an x plus 4. And I'm left with x plus 4 minus x times 2, or 2x. If you're not seeing that, that comes from there. Like the 16 was factored out, the x plus 4 was factored out. So that's all that was left in this second part, right? I factored this and this. Over x plus 4 all to the 4th. And then I notice that this and this cancel, I get a 4. If you haven't noticed this yet, and if I haven't pointed it out, or if it hasn't been pointed out to you, if this started degree 2, it should always be degree 3, one more. That will always happen. Depending on how you did it algebraically, it may or may not look like that, but that always happens. Okay, so I'll eventually get a 3 there because I had a 2 there. And then cleaning it up. So 16, I want to leave it factored. 4 minus x over x plus 4 all cubed. Where does the derivative equal 0? When x equals 4. That's when I plug 4 in here and I get 0 on top. So that's when the derivative is 0. Where does the derivative not exist? At x equals negative 4. That's where the bottom is 0. And from before, we haven't really had to consider this yet with curve sketching, but that's something that we did before. Now, I notice that that's an asymptote. So I already kind of know there's something weird happening there, but it's still important to include that. We're going to include it in our table. And something that we need to know is there are other cases where the derivative does not exist, not just where there's an asymptote. So we can't just ignore it or always assume that it's an asymptote, but often it will be. Okay? Okay, start building our table. X. I'll use y. Y prime and y. So when x is less than -4, and then at -4, and then between -4 and 4, and then at 4, and then when x is greater than 4. And I just start plugging these in. Okay, and I want to know what the derivative is doing. So I know here it does not exist, and I know here it's 0. What's happening here? So I'll put in some value in that interval. I'll pick -10, and it looks like I get a positive on top and a negative on bottom because the bottom is now cubed. So -10 plus 4 is -6. -6 cubed is negative. And 4 minus -10 is 4 plus 10, so that's going to be positive. So this is negative, which tells me it's decreasing. That's the whole point of what I wanted to do here. Does not exist. Pick a value in this interval. How about 0? That makes it easy. The top is positive. The bottom is positive. So the whole thing is positive, so it's increasing. And then it's 0. And then I'll pick 10. 4 minus 10. So now the top is negative and the bottom is positive. So again, this is negative, so this is decreasing. So I had increasing and then 0 and then decreasing. So that's a local max. And I'm going to figure out what f at 4 is. And when I plug it in, it works out to be a nice value of 1. That doesn't always work out that way. So I have a max at 4, 1. And that's plugged into the original value, or the original function. That's what we care about. That's not plugging it into the derivative. That's plugging it into the original. Okay, that's all the pre-work we need to do. Often it's actually more than that in order to draw a sketch. But now I've got everything, and so we can start doing our sketch. And again, the order that you start doing this is not super important. I've got an intercept at 0, 0. I want to look at where I have a vertical asymptote. I only have the one in this case. And it was at -4, isn't that right? So I got a vertical asymptote at -4. And I got a horizontal asymptote at 0. Okay. And what else do I have? I've got a point over here at 4, +1. That's a local max. And I guess I can label the rest of my graph. So this is y, x. Okay. Starting with my asymptotes. As I approach the asymptote from the left, I'm going to -infinity. So it's going to come down here. And from the right, it's going to be -infinity. And as I'm approaching my horizontal asymptote, going to the left, it's approaching from below. So this curve is going to look like this. And stay below the asymptote and go down like that. This one approaches from above, and I can see that it has a local max that's above the asymptote. So this one, and it goes through there. I'm trying to make that look like it is, in fact, a maximum. I did okay there. You know, if you ever make a mistake, it is totally worth redrawing to make it look nice. And I'm just going to label my asymptotes here. So this is y equals 0. This is x equals -4. We always want to mark where our asymptotes are exactly. And my rule of thumb is if you only have one sketch on a grid, you don't have to label it. But if we were, it would be y equals that big thing that we started with. And I do think that that's about everything. There's our sketch. Okay. So that's it.